Every app you use, every video you watch, and every text you send relies on one incredibly rigid choice. Deep inside your computer, everything is forced to pick a side. Information is stored in tiny units called bits. You can think of a bit exactly like a physical light switch. It can be completely off, which we call a 0, or completely on, which we call a 1. There is absolutely no halfway. But researchers building quantum computers use a different kind of building block. It is called a quantum bit, or qubit for short, and it ignores that rigid rule. A qubit can be a 0, it can be a 1, or it can be a blended mix of both 0 and 1 at the exact same time. This creates an immediate problem for the scientists trying to build these machines. How do you draw a picture of an object that exists in two opposite states simultaneously? To make sense of this behavior, they had to invent an entirely new kind of visual map to track where these qubits actually are. They call this map the Bloch Sphere. The name sounds intimidating, but it is simply a 3D globe. Think of it like a miniature planet, and its entire job is to show us exactly what a single qubit is doing. This diagram maps it out. A classical 0 sits at the very top, exactly at the North Pole. A classical 1 maps to the bottom, the South Pole. The space between means the qubit is a mix of 0 and 1, a state called superposition. So when you hear researchers talk about the state of a qubit, they are really just talking about a specific location on the surface of this tiny planet. But if a qubit is lost somewhere out in that massive space of superposition, how does a programmer actually pinpoint its exact location? This image shows the mathematical formula scientists use to track it. Looking at all those Greek letters and symbols, it is easy to feel overwhelmed. Those Greek symbols, theta and phi, act exactly like latitude and longitude lines, tracking a glowing dot on our globe. Resting on the equator means a perfect 50-50 mix of 0 and 1. Sliding into the northern hemisphere means it leans heavily towards 0. These equations serve as a quantum GPS system, providing the exact coordinates for our glowing dot. This concept is what those notes call a geometrical interpretation. That just means taking invisible, abstract quantum behavior and representing it as a physical dot floating in 3D space. This gives quantum programmers a concrete way to work. When they sit down to write code to perform quantum operations, they aren't blindly guessing. Every command they give moves that dot across the surface of the Bloch sphere to a specific new coordinate. The math running the machine is dense and difficult to imagine, but the visual map we use to control it is beautifully simple. The next time someone uses intimidating jargon about quantum states, remember they are just talking about finding a location on a very small, very special map.